A Brief History of Time, written by Stephen Hawking, read by Akash Veer. This is Chapter 6, Black Holes. The term black hole is of very recent origin. It was coined in 1969 by the American scientist John Wheeler as a graphic description of an idea that goes back at least 200 years, to a time when there were two theories about light. One, which Newton favored, was that it was composed of particles. The other was that it was made of waves. We now know that really both theories are correct. By wave-particle duality of quantum mechanics, light can be regarded as both a wave and a particle. Under the theory that light is made up of waves, it was not clear how it would respond to gravity. But if light is composed of particles, one might expect them to be affected by gravity in the same way that cannonballs, rockets, and planets are. At first, people thought that particles of light travel infinitely fast, so gravity would not have any effect, or gravity have not been able to slow them down. But the discovery by rumor that light travels at a finite speed meant that gravity might have an important effect. On this assumption, a Cambridge don, John Michell, wrote a paper in 1783 in the Philosophical Transaction of the Royal Society of London, in which he pointed out that a star that was sufficiently massive and compact would have a strong gravitational field that light could not escape. Any light emitted from the surface of star would be dragged back by the star's gravitational attraction before it could get far away. Michell suggested that there might be a large number of stars like this, although we would not be able to see them because the light from them would not reach us. We would still feel their gravitational attraction. Such objects are what we now call black holes, because that is what they are, black voids in space. A similar suggestion was made a few years later by the French scientist the Marquis de Laplace, apparently independent of Michell. Interestingly enough, Laplace included it in only the first and the second edition of his book, The System of the World, and left it out of later editions. Perhaps he decided that it was a crazy idea. Also, the particle theory of light went out of favor during the 19th century. It seemed that everything could be explained by the wave theory, and according to the theory, it was not clear that light would be affected by gravity at all. In fact, it is not really consistent to treat light like cannonballs in Newtonian theories of gravity, because the speed of light is fixed. A cannonball fired upward from the Earth will be slowed down by the gravity and will eventually stop and fall back. A photon, however, must continue upward at a constant speed. How then can Newtonian gravity affect light? A consistent theory of how gravity affects light did not come along until Einstein proposed general relativity in 1915. And even then, it was a long time before the implications of the theory for massive stars were understood. To understand how a black hole might be formed, we first need an understanding of the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen, starts to collapse in on itself due to its gravitational attraction. As it contracts, the atoms of the gas collide with each other more and more frequently and at greater and greater speeds. The gases heats up. Eventually, the gases will be so hot that when the hydrogen atoms collide, they no longer bounce off each other, but intense coalesce to form helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes the stars shine. This additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction, and the gas stops contracting. It is a bit like a balloon. There is a balance between the pressure of the air inside, and which is trying to make the balloon expand, and the tension in the rubber, which is trying to make the balloon smaller. Stars will remain stable like this for a long time, with heat from the nuclear reaction balancing the gravitational attraction. Eventually, however, the star will run out of its hydrogen and other nuclear fuel. Paradoxically, the more fuel a star off with, the sooner it runs out. This is because the more massive the star is, the hotter it needs to be to balance its gravitational attraction. And the hotter it is, the faster it will use up its fuel. Our sun has probably got enough fuel for another 5,000 million years or so, but more massive stars can use up their fuel in as little as 100 million years, much less than the age of the universe. When a star runs out of fuel, it starts to cool off and so to contract. What might happen to it then was first understood only at the end of the 1920s. In 1928, an Indian graduate student, Subramaniam Chandrasekhar, set sail for England to study at Cambridge with the British astronomer Sir Arthur Eddington, an expert on general relativity. According to some accounts, a journalist told Eddington in the early 1920s that he had heard there were only 3 people in the world who understood general relativity. Eddington paused, then replied, "I am trying to think who the third person is." During his voyage from India, Chandrasekhar worked out how big a star could be and still support itself against its own gravity after it had used up all its fuel. The idea was this: when the star becomes small, the matter particles get very near to each other, and so according to the Pauli exclusion principle, they must have very different velocities. This makes them move away from each other and so tend to make the star expand. A star can therefore maintain itself at a constant radius by a balance between the attraction of gravity and the repulsion that arises from the exclusion principle, just as earlier in its life gravity was balanced by the heat. Chandrasekhar realized, however, that there is a limit to the repulsion that the exclusion principle can provide. The theory of relativity limits the maximum difference in the velocities of the matter particles in the star to the speed of light. This means that when the star got sufficiently dense, the repulsion caused by the exclusion principle would be less than the attraction of gravity. Chandrasekhar calculated that a cold star of more than about 1.5 times the mass of the Sun would not be able to support itself against its own gravity. This mass is now known as Chandrasekhar limit. A similar discovery was made about the same time by the Russian scientist Lee Davidovich Landau. This had serious implications for the ultimate fate of massive stars. If a star's mass is less than the Chandrasekhar limit, it can eventually stop contracting and settle down to a possible final stage as a white dwarf, with a radius of a few thousand miles and a density of hundreds of tons per cubic inch. A white dwarf is supported by the exclusion principle, repulsion between the electrons in its matter. We observe a large number of these white dwarf stars. One of the first to be discovered is a star that is orbiting around Sirius, the brightest star in the night sky. Landau pointed out that there was another possible final state for a star, also with a limiting mass of about 1 or 2 times the mass of the Sun, but much smaller even than a white dwarf. these stars would be supported by the exclusion principle repulsion between the neutron and protons rather than between electrons. They were therefore called neutron stars. They would have a radius of only 10 miles or so and a density of hundreds of millions of tons per cubic inch. At the time they were first predicted, there was no way that neutron star could be observed. They were not actually detected until much later. Stars with masses above the Chandrasekhar limit, on the other hand, have a big problem when they come to the end of their fuel. In some cases, they may explode or manage to throw off enough matter to reduce their mass below the limit and so avoid catastrophic gravitational collapse. But it is difficult to believe that this would always happen, no matter how big the star. How could it know that it had to lose weight? And even if every star managed to lose enough mass to avoid collapse, what would happen if you added more mass to a white dwarf or neutron star to take it over that limit? Would it collapse to infinite density? Eddington was shocked by that implication, and he refused to believe Chandrasekhar's result. Eddington thought it was simply not possible that a star could collapse to a point. This was the view of most scientists. Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. The hostility of other scientists, particularly Eddington, his former teacher and the leading authority on the structure of stars, persuaded Chandrasekhar to abandon this line of work and turn instead of other problems in astronomy, such as the motion of star clusters. However, when he was awarded the Nobel Prize in 1983, it was at least in part for his early work on the limiting mass of cold stars. Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than Chandrasekhar limit. But the problem of understanding what would happen to such a star according to general relativity was first solved by a young American, Robert Oppenheimer, in 1939. His result, however, suggested that there would be no observational consequences that could be detected by the telescopes of the day. Then the Second World War intervened, and Oppenheimer himself became closely involved in the atom bomb project. After the war, the problem of gravitational collapse was largely forgotten, as most scientists became caught up in what happened on the scale of the atom and its nucleus. In the 1960s, however, interest in the large-scale problem of astronomy and cosmology was revived by the great increase in the number of and range of astronomical observations brought about by the applications of modern technology. Oppenheimer's work was then rediscovered and extended by a number of people. The picture that we now have from Oppenheimer's work is as follows. The gravitational field of a star changes the path of light rays in space-time from what they would have been had the star not been present. The light cones, which indicate the paths followed in space and time by flashes of light emitted from their tips, are bent slightly inward near the surface of the star. This can be seen in the bending of light from distant stars observed during an eclipse of the sun. As the star contrasts, the gravitational field at its surface gets stronger and the light cones get bent inward more. This makes it more difficult for light from the star to escape, and the light appears dimmer and redder to an observer at a distance. Eventually, when the star has shrunk to a certain critical radius, the gravitational field at the surface becomes so strong that the light cones are bent inward so much that light can no longer escape. According to the theory of relativity, nothing can travel faster than light. Thus, if light cannot escape, neither can anything else. Everything is dragged back by the gravitational field. So, one has a set of events a region of space-time from which it is not possible to escape to reach a distant observer. This region is what we now call a black hole. Its boundary is called the event horizon, and it coincides with the path of light rays that just fail to escape from the black hole.